So this video will be going over Chapter 1, Matter and Measurements, Section 1.1, 1.2, and 1.3. So first, let me ask you a question. Anything in the universe can be classified into two categories. Can you tell me what are these two categories? So you can pause to think about it. So the two categories that anything in the universe can be classified into are matter and energy. And matter is studied by chemistry, or in other words, chemistry is the study of matter, and physics is the study of energy. So this course is about studying matter. We will have to deal with energy because matter is affected by energy. And so this first chapter will introduce you to matter and measurements. So chemistry, the definition we can have for it is that it's the study of matter, its composition, properties, and transformation. And matter, what is matter? It's anything that has mass and takes up volume. So matter can be anything that you find in nature, like fruits, trees, plants, rocks, water, cotton, anything that is naturally occurring in nature. And matter comprise also anything that has been synthesized by the humans. We produce a lot of new materials, composite materials, medications, food. And we also ourselves are matter. We are living matter. What I described earlier was mostly non-living matter. Plants are living matter. Anything that grows is living matter, but rocks, for example, and water by itself are not living matter. So matter is anything that has mass and takes up volume. There are three states of matter: the solid state, the liquid state, and the gaseous state. We will start looking at the solid state first. So by definition, we recognize a solid state because when matter has a definite volume, when the volume is definite and doesn't change, you cannot compress it or expand it. That's what it means to have a definite volume. Solids also maintain their shape regardless of the container they're put in. So like a rock will keep its shape. Wood will keep its shape. So solids will keep their shape. And now if we look at the arrangement at the atomic level or at the molecular level, the reason why solids has these properties, it's because their particles lie close together. And so in this example, so they lie close together in a regular pattern. In this model here on the right side, it's a model of ice, water as a solid. So water is H2O, two hydrogen atoms represented in white balls here, and one oxygen atom represented in red. And so we have many water molecules represented in this model. And you can see some lines going diagonally from the lower left corner to the upper right corner. And so that shows you how the molecules of water are arranged in lines here. So there is a pattern. They are not randomly put together. They are arranged in a pattern and they follow that pattern. So it's orderly, organized. And so that's what you would recognize a solid from. It's because it has an organized arrangement at the molecular level or atomic level. And that's why that arrangement stays, doesn't change, and that's why the solids keep their shape. And also that the volume doesn't change. In the liquid state, the volume is still definite, so that means you cannot compress or extend the volume of a liquid. However, compared to a solid, as opposed to a solid, it takes the shape of the container. The solid will take the shape of the container and flow around and take the shape of the container. So if you pour some liquid into a cylindric container, it will take the shape of the cylindric container. If instead you put it in a rectangular container, it will take the shape of the container. And so at the molecular level, liquid particles are close together, just like in solids, but they can move past one another. And so their arrangement is random. There is no lattice or pattern in a liquid. The particles are packed together. They're very close together, as you can see in this model. The molecules of water are packed together, but you don't see anymore that organized pattern you saw earlier. And so they are randomly put together and they can move past one another. So there is more movement allowed in a liquid compared to a solid. So they can move around each other, and that's why they can roll around each other, and that's why liquid flows. They can flow. In the gas state, the gas has no definite shape. So again, like liquid, there is no definite shape, and it will assume the shape of the container. So if you have a cylindrical container, it will be taking all that volume. However, compared to liquids, a gas has no definite volume. So that means you can expand the volume of a gas or compress the volume of a gas. That's what distinguishes the gases very much from the other two, solid and liquid state. And so if you look at the molecular level or atomic level, you see the molecules of water, and here there is very few of them. There is only 4 of them represented in that model. And you can see that they are not packed anymore together, right? There's a lot of empty space between the molecules. The gas particles are very far apart from each other, and they can move around, and they move around constantly and randomly. There is no pattern in their movement. They just go in a straight line until they hit something, and then they bounce and move in another direction. But there is very little matter in a given amount of volume, as you can see. There is much less molecules than earlier when we had the solid or the liquid. So now we will talk about physical properties. Physical properties of matter can be observed or measured without changing the composition of the material. So changing the composition means changing the identity. You're not able to change the identity of your material when you are looking at the physical property. So obvious physical properties are properties of color, odor, so you can detect those and find them without changing the composition of the material. State of matter, which means is the substance in a solid state, liquid state, or gas state. Other examples of physical properties are the boiling point. The boiling point represents the temperature at which the liquid substance will turn into a gas. So because the liquid is not changed except from its state of matter going from liquid to gas, it's a physical property. We still have the same substance before and after the boiling point. So that's a physical property. Same thing with the melting point. When you're melting a substance, it's the same substance before and after. It's just the state of the matter that is different. Solubility is also a physical property. For example, when you are dissolving salt in water, you can retrieve your salt and waters separately. So even though salt is in water, it's still the same molecule, and it doesn't change the composition of the material. We still have salt and water. And so the solubility of salt when it dissolves in water represents a physical property. Conductivity is also a physical property. For example, imagine a copper wire, a wire of metal copper. When you are having electricity going through it, this makes the electrons within the metal move, but this movement doesn't change the identity of the metal. When you are conducting electricity through copper, it is still copper when you are doing it, and it's still copper after you've done conducting electricity through it. So conductivity is a physical property. It does not change the composition of the material. So now let's talk about changes. And so physical changes. Earlier we were going over physical properties. Now physical changes, it's when you are altering the material without changing its composition. And so easy examples that can illustrate that are phase changes. When, for example, you're changing a solid into a liquid. Like, let's look at water. On the left side here, we have solid water. When we are melting it into liquid water, this is a physical change. Melting is a physical change because because water went from a solid to a liquid, changed state of matter, but it's still water, still the same substance. So that's why it's called a physical change. The composition of the substance is still the same. And so you could argue the same with the boiling. When you are changing liquid water into water vapor, it's still water before and after. It's only the state of matter that has changed. You go from a liquid phase to a vapor phase. So boiling is a physical change. So physical change will be covered in more details in chapter 7. Now, we also can describe chemical properties for substances, and these chemical properties describe the ability of a substance to interact with other substance or to change into a new substance. So when you describe a chemical property, you're describing the ability of a substance to become another one through a chemical change. So it explains that they will react with other substances and become another substance. So examples of chemical properties include flammability. For example, liquid is very flammable when, for example, if you bring a spark close to a flammable liquid, it can catch on fire and burn. And when a liquid burns, it's getting transformed into new substances, and you're using it and decomposing it into something different. So flammability is a chemical property because of that. Toxicity is another example of a chemical property, because when something is toxic, it's usually because it reacts with, for example, toxic to a human means, for example, that substance will react with the water in your body and become a dangerous substance. Or react with other molecules within your body and make, toxic substances. So it's all of these that are called chemical properties, reactivity with other molecules. Chemical change is when you are making the substance go through a change that is chemical, and that means it's a chemical reaction. Chemical change, you really should see it as a chemical reaction. It's when you are converting one substance into another. And so that's the main thing that we chemists study, right? We write chemical equations which represent chemical reactions, which are chemical changes. It's when you are changing a substance into other and new substances. So when a chemical change takes place, the original substance is turned into one or more new substances with a new composition and new physical and chemical properties. In the example shown here, on the left side we have oxygen. It's the diatomic molecule made of 2 atoms of oxygen, red. And the hydrogen molecule is also a diatomic molecule made of 2 white hydrogen atoms together. And so hydrogen and oxygen can react together, and they react very strongly together. If you bring a spark into a mixture of oxygen and hydrogen, it will explode. It's a very explosive reaction, and you will produce water, the molecule of water on the right side, H2O, made of 2 hydrogens and 1 oxygen. And so this reaction looks very simple, right? H2 plus O2 gives H2O, water. And but it's a very, very powerful reaction that is actually used to send shuttles into space. So you see, chemical changes are used to do amazing things. And chemical reactions are happening within you, and that's what makes you alive, right? It's because there are chemical reactions happening within you that you're alive. So let's go through a learning check now. And I want you to classify each of the following changes as physical or chemical. So you have a list here of changes, and you need to decide if they are physical or chemical. You can pause the video now and do the work before you look at the answers. So, burning a candle. So burning a candle, is it chemical or physical? When you're burning the candle, the wax that you're burning, it seems to disappear in the air, right? And so what happens is that it's decomposed into gases that are escaping into the room. So that's why you don't see anything anymore. So burning a candle is a chemical change. Ice melting on the street. So when ice is melting due to the sun warming the ice, the ice becomes a puddle of water, right? And ice, you know that it's also made of water. So you go from solid water to liquid water. So that's a physical change. Toasting a marshmallow. Toasting a marshmallow, your marshmallow, you know, marshmallows are white and fluffy, and when you place them into a flame, they become brown and eventually even black. And so it's not a marshmallow anymore, you've burned it, right? So when you're burning something, you are decomposing it. And in the case of the marshmallow, the black that is left afterwards is the carbon and there's a lot of gases that have been escaped into the air that you don't see maybe, but they have gone, and so your marshmallow has become something else. So that's a chemical change. Cutting a pizza, making slices of pizza, um, is a physical change, right? You're not changing the pizza into something else, you're just cutting it into smaller pieces. Iron rusting in an old car. Um, so an iron nail is like shiny metal, uh, gray, right? Gray metal. And when it's rusting, it's not that color anymore, right? When it's rusting, it becomes a brown, flaky or powdery substance, brown orange, right? And that you can uh, uh, scrape, right? It becomes pieces that you can remove. So it's not holding it into one piece like iron would do. So iron rusting in an old car, it when you have the rust, it's not iron anymore. It's a new substance that has a different color, that has different physical properties. So that's a chemical change. Water droplets condensing on a window. So the steam or water vapor that is contained in a room sometimes will deposit into the window pane and condense. So condensing means you're going from the physical state of vapor to physical state of liquid. So you have vapor water that condenses into liquid water, but you start from water and you end up with water. So that's a physical change. And so here are all the answers. So, classification of matter. All matter can be classified as either a pure substance or a mixture. So let's look at pure substances first. A pure substance is composed of only a single component, so one type of atom or one type of molecule. And when you're talking about a pure substance, it's always that same type of atom or that same molecule. So you can give it a formula. It has a constant composition, and this is represented by formulas. For example, when you're talking about oxygen, which is a pure substance, its formula will be O2, two atoms of oxygen bonded together. If you're talking about a molecule like water, its formula will be H2O, and H2O is water. So it's representing that pure substance and no other. And it doesn't matter the size of the sample or the origin of the sample, it's always the same formula. So water that you find here in your home is the same formula than if you found water on the other side of the earth, okay? Another characteristics of pure substances is that they cannot be broken down to other pure substances by a physical change, right? It's physically you cannot break them down. They will stay as they are pure substances. So pure substances can be subclassified as elements or compound. Elements are pure substances that cannot be broken down by a chemical change. So elements are all found in the periodic table. If you are familiar with the periodic table, and you will be, all the elements are listed in there. It's all the elements that are found in nature. For example, aluminum is one element, and when you have aluminum foil in the kitchen, for example, this is a pure substance. It's just made of aluminum atoms. And if we were able to see at the atomic level, we would see only atoms of aluminum packed together. And so here it's a solid. So notice how it's packed together in an organized fashion. You can see a pattern. And so that represents a solid. So you cannot break down aluminum into something else by a chemical change. It's not possible. In the periodic table, you will also see other elements that are diatomic elements, even though on the periodic table they look like they are classified as one atom. In nature, they're found as diatomic molecules, and those are hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. And so nitrogen is a pure substance. It's made of two nitrogen atoms bonded together. So that's why the formula is N2. And nitrogen is represented by blue balls here. And so that's another example of an element that cannot be broken down by a chemical change. So again, pure substances can be classified as elements or compound. Whenever you have a compound, it's because you have two or more elements that are combined chemically. They are joined and bonded into a definite ratio. And that's why we can write a formula for them, because that definite ratio gives you a formula for your compound. As an example, water is a compound. It's made of oxygen atoms and two hydrogen atoms bonded together. So the formula is H2O. And when you have pure water, that's the only molecule you have in there. It's H2O all over the place. So that's a compound made of at least two elements bonded together into the same ratio. Another example with table salt. Table salt is made of sodium and chloride, the chloride ion from chlorine. And so Na is the symbol for sodium, Cl is the symbol for the chloride ion. And so when you put them together, it's the solid NaCl, which is table salt, a common substance. But it's a pure substance. It's made of only NaCl. And all those grains are made of just sodium and chlorine in a ratio of 1:1. For one chlorine, you have one sodium. So if we back up a little bit here, so all matter can be classified as either a pure substance or a mixture. And we went over what pure substances are. Now let's look at what mixtures are. Mixtures are composed of more than one substance that are physically mixed but not chemically bonded. So as opposed to compound, when you have a mixture, you have more than one substance and they are not bonded together. So you cannot give them a formula. It's going to be instead, water and salt together, for example. And they would be physically mixed. So molecules of water near, sodium and chloride ions, very well mixed, but they are not bonded, chemically bonded. And so you cannot give them a formula. And mixtures can have varying composition. For example, if we take the example of salt and water, you can have more or less salt in the water. So you can have just a few grains of salt in the water, in a glass of water, for example, or you can have a full spoon of salt in a glass of water. So their composition is varying. That's why you cannot give it a definite formula. It can change, and it always changes depending on the mixture you're preparing. And so mixtures can be, I gave an example of a solid in a liquid, but that can be a gas in a liquid, or a solid into a solid, or a liquid into a liquid, or mixtures of gases, right? Um, Mixtures can be separated into their component by physical changes. So, for example, if we go back to our example of table salt dissolved in water, you can physically separate them and retrieve your component, the two pure substances. So, in the example of table salt in water, to retrieve the salt, you would have to evaporate the water. So you would heat the mixture, the salted water, and the water would evaporate, and the salt would crystallize into the container. So you would get back your crystals of salt. Another obvious way to separate mixtures is, for example, filtration. If you have a solid into a liquid, but a solid that is not soluble into that liquid, you can retrieve the solid by filtration. If you, for example, separate sand from water using filtration. So that's mixtures. Let's look at the mixtures more closely. So these here, again, that's pure substances, right? Here we have table sugar, C12H22O11, and water, H2O. They are both pure substances because you can see here we have formulas for them. And so when you're talking about table sugar, it's always the molecule made of C12 carbon, 22 hydrogens, and 11 oxygens. And then water is made of 2 hydrogen and 1 oxygen. And so these are two pure substances, right? Now, if we mix them together, we get a mixture, right? Because we have more than one substance mixed together. And sugar will dissolve in water to make an homogeneous mixture. And so the sugar is among molecules of water, it's dissolved. And so instead of having the sugar packed into a crystal, all the molecules packed together and forming a solid, now they are separated and floating into the water. So that's a mixture. But the molecules of water and the molecules of sugar are not bonded. They are freely moving next to each other. And so when you have a mixture, you can classify mixtures as homogeneous or heterogeneous, depending if they look like one substance or not. And so on the left side here, we have a picture showing an homogeneous mixture of simple sugar, or simple syrup, sorry. And to the left of it, there is a model showing how the molecules, the two different molecules, some are represented in green, the others are in purple. And you can see how they are very well mixed, right? Next to a green molecule, you see purple molecules, and then beyond that, again, a green molecule. And it's very well mixed together. However, there is no bonds between them, right? It's mixed but not bonded. So that's why it's called a mixture. And it's called homogeneous because it looks uniform. It looks like one substance. So if you were not told what you have in that liquid, you could take this as a pure substance. But if you are told that it's a mixture of sugar and water, for example, then you know it's an homogeneous mixture. So homogeneous, homo means the same. So it's a mixture that looks the same as if it was one substance. On the right side, we have a picture showing an heterogeneous mixture. And vinaigrette here is the example. Vinaigrette is made of vinegar. So the vinegar is the layer at the bottom of the jar, and the oil is the layer on top. Why is vinegar on the bottom and oil on top? It's because of their densities. The vinegar has a higher density than oil, and that's why it goes to the bottom. But you can see that they are forming two layers. They are separated into two layers. And that's what we call an heterogeneous mixture, because they are not looking like one substance. You can definitely tell there is two substances there. So that's why it's called an heterogeneous mixture. And if you look at the model to the right of the picture, you can see that this time the purple balls are definitely sitting on top of the green balls. So they are not well mixed at the molecular level. They are really separating, and as each type is staying on its side. And so hetero means different. So an heterogeneous mixture is a mixture where you can see the different parts. You can see that it's made of different substances mixed together. So they are the easiest to recognize because it's physically visible that they are mixtures. So this flow chart is showing you what we just covered, the classification of matter. So starting from the top, matter can be classified into pure substances or mixture. Pure substances can be classified into elements or compound. You have an element when it's only made of one kind of symbol, one element, only one type of atom. Here, for example, copper. A penny is only made of copper atoms. A compound is made of the same molecule everywhere, and water is an example of a molecule. And when you have pure water, it's just molecules of H2O. So that's a compound because you have two types of atoms in there, the H and the O, the hydrogen and the oxygen, bonded in a very specific ratio of 2:1. 2 hydrogens for 1 oxygen. And then matter can be classified as pure substances or mixture. Mixtures can be further classified as homogeneous or heterogeneous. It's homogeneous when you cannot tell that it's made of more than one substance. From the outside, it looks like one substance, even though you know it's made of more than one. And this example here is a solid homogeneous mixture, brass. Brass is made of copper and zinc, and their proportions can vary. And so here it's showing you how they are mixed very well. For every copper atom, you have another zinc around. So it's mixed at the atomic level. So that's why it looks like one substance, but you know it's made of two at least. And an heterogeneous mixture, you can definitely tell there's two substances in there. The copper at the bottom, the pennies, and then the water on top. And so heterogeneous mixtures look like, you know, the substances are really visible in there, and you can see the different parts and the different type of substances there. So let's do a learning check of what we just covered here and identify each of the following as a pure substance or a mixture. If it's a pure substance, specify if it's an element or a compound. And if you decide it's a mixture, specify if it is homogeneous or heterogeneous. Again, you can pause the video now to think about this before hearing and watching the answer. So, when we have pasta and tomato sauce together, is this homogeneous? Oh, sorry, is this a mixture or a pure substance? So you can definitely tell apart the pasta from the tomato sauce, right? So that looks like a mixture. And because you can definitely tell them apart, it's an heterogeneous mixture. Tinfoil, is it a pure substance or a mixture? So tinfoil is actually what was used before aluminum foil, and tin is an element. It's a metal that can be found in the periodic table. Element symbol is Sn, and so tin, because it says tin here, which is Sn, it's only one type of atom, and so that will be a pure substance, and it's only one element, so it's it's an element. So it's a pure substance and an element. Helium also found in the periodic table. So really when you want to decide if you have an element or not, you want to have the periodic table before your eyes. And so helium is an element found in the periodic table on the upper right corner. It's He. Helium is a noble gas made of just helium atoms, so that's an element, a pure substance and an element. Air. So the air you breathe is a mixture of gases. In air, you find oxygen, nitrogen, so mainly nitrogen, then oxygen, and then many other gases in smaller amounts, like carbon dioxide, water, argon. So it's a mixture, right? However, it's a mixture, but you cannot really tell that it's a mixture of gases. What you see is nothing, right? Air is invisible to the eye, but there is matter there. There are gases that have mass, floating around us. So, and there are different gases. There is oxygen, nitrogen, at least. So they look like one gas, if you will. You cannot tell them apart. You cannot see them even. So that's an homogeneous mixture. Ocean water. So ocean water looks like water, right? You cannot really tell that there is a lot of salt in there, right? So ocean water is made of water and salt, because you know that it's salted. But you cannot tell that there's salt in there. You cannot visibly see it. So it's an homogeneous mixture. The rust on an iron nail. So if we look at the rust only, not the rust plus the iron nail, just the rust. So is this pure substance or a mixture? So if you look at just the rust, it's a pure substance. We can give it a formula. It's not given there, but the formula of rust is Fe2O3, iron 3 oxide. And so you can give it a formula, and I told you it's iron 3 oxide. So there is iron and there's the oxide. So it's made of at least two elements. It's made of oxygen and iron. So the rust is a compound. It's a pure substance. You can give it a formula, and the formula has more than one element. So that's a compound, a pure substance compound.